Welcome to AP Physics. Yesterday, we were pondering applications of induction, and we ended by pondering an electromagnetic wave. When you vibrate an electron, that's a changing electric field, which causes a changing magnetic field, which causes a changing electric field, etc., and that propagates as an electromagnetic wave. Here I have a simulation that's going to address that in a little bit different fashion. So we have a charge here. It's a positive charge, not a negative charge, but it's still a charge. And we have those white lines going outward from it. That is the electric field. If I reinitiate it, what I want you to notice is it travels out, and any change in that electric field is going to propagate at the speed of light. If I now take my charge and I move it, that was just way cool. We have to do that again. When we move that charge, that's a changing electric field, and that changing electric field propagates out, and you see that as the wave that travels out. That's the electric field component of an electromagnetic wave. Now, this simulation is not showing the magnetic field component. You'll have to imagine that. If we just bump our charge, we get that field. If we get it vibrating in a sinusoidal function, we get a regular wave that travels out. If we move it circularly, again, we get a wave that travels out. I just prefer the manual bumping of the charge. So the point I'm trying to make as I'm having fun here with the simulation is when you move a charge, you change the electric field. That propagates through space. That is the initiation of a wave. In an atom, when an electron is bumped, when it vibrates between shells, that's a changing field, and that's what initiates your electromagnetic wave. The demonstration I have set up here involves a radio in the broadcast of electromagnetic waves. So normally when we have a radio, there are electromagnetic waves, radio waves that are being broadcast through the air, and what that does is that jiggles the electrons in the antenna, and through the electronics in the radio, okay, that signal comes to the speaker, jiggles the electrons. You have an alternating electric current in the pattern of the signal, and through the interaction of that current and the magnets in the speaker, you wiggle the speaker membrane and the speaker produces sound. So if we turn on our radio, we'll turn our volume. So we are now receiving the signal, wiggling the electrons in here, vibrating the speaker membrane. Now if I turn our volume down a little bit, on the other side, over here, connected to the other jack of the speaker, I have a solenoid. So then when I turn on our volume, the one side with the speaker, which you can't see anymore, is producing sound. I'm going to flip my balance to the other side. And now what I'm doing is I'm wiggling the electrons in here. Well, that varying electric current in the wires of the solenoid is setting up a changing magnetic field, a d phi dt in the core of the solenoid. So we are broadcasting that radio signal out into the air. On the speaker, it was converting it into sound waves. On this side, it's converting it into an electromagnetic wave. So we have our own little mini radio broadcaster right here. A little bit further over, I have another solenoid, and this solenoid is connected. Have to make a little more room here. This solenoid is connected to a miniature amplifier. So we are still broadcasting these waves. So now let's see if we can tune in the radio signal that we're broadcasting through here, through this solenoid, into the second solenoid right here. So everything is hooked up. I'm going to turn up our volume on our little amplifier. I'm going to turn up the volume over here. Hopefully you can hear the sound there. This demonstration is much better live. But basically what we are doing is we are shaking the electrons in this, producing a changing magnetic field. That changing magnetic field is on this solenoid. That d phi dt is inducing an EMF or a current in the coils here, and that signal is then being converted into sound energy by our little speaker. That's a basic idea of radio broadcast. You are just taking a radio antenna and you are wiggling the electrons in that radio antenna in the pattern of the signal and the information you want to broadcast. It is then wiggling the electrons in whatever antenna of whatever source that is trying to receive, and that signal is being converted back. That's the same idea of what happens in your cell phone communications. Your cell phone broadcasts an electromagnetic wave by wiggling the electrons, and that signal is then received by a broadcast tower, or vice versa. The tower broadcasts the signal and your phone receives it. It's all transmission of electromagnetic waves. Chapter 32, Inductance. Here we have a simple circuit, just a battery and a resistor and a switch. So when we take this switch and we close it, think about what happens. Before it's closed, there's no current because there's no path. After it's closed, there is current. There is a value for the current. So you went from zero current to all of a sudden there is a current. Well, that's a changing current in a loop. And if you have a changing current in a loop, you're going to produce a magnetic field, and that magnetic field is going to be changing. If that magnetic field is changing, then you have a changing flux in that loop. And if you have a changing flux in that loop, we induce an EMF. We'll stay in the algebra range here. We induce an EMF, emphasizing Lenz's law, the negative. We induce an EMF that fights the change that caused it. Well, now let's go back to our circuit loop. From the actual circuit, when we close that switch, high potential side, low potential side, we're going to cause a current to flow around in this direction. Right hand rule, if you wrap your right hand in that clockwise direction, you will cause a magnetic field into the page. And that's by the actual loop of the circuit itself. You induce a back EMF fighting this change. That back EMF is going to oppose that, so then it's going to induce a backwards magnetic field or an induced EMF that fights the change or is counterclockwise. This idea is called self-inductance. Now, for a simple circuit, it doesn't make a whole heck of a lot of difference because there's just not enough there. The change will be opposed ever so briefly, but generally for a simple circuit, we will just ignore it. But if you have a circuit where you have more loops, say like a solenoid, then that self-inductance becomes important. In general, let's define self-inductance. It is basically that back EMF that is induced to oppose the original EMF. This original EMF is a battery. I don't want to say it's always going to be a battery, but in this case, it is a battery. Now, if we think about that back EMF, the self-inductance, that back EMF is going to be related to the current, but not just the current, the change in the current. It's going to be proportional to a di dt. If we're going to set up an equation, all we need is a proportionality constant. So let's define our proportionality constant. Inductance, symbol L. And so then we can set up the equation that induced back EMF. It's opposing, so negative, Lenz's law is still there, negative L di dt. Now, if we consider a simple circuit, there's our simple circuit with an EMF from the battery and a resistor. Well, we know from Faraday's law, EMF is equal to negative N d phi dt. Think of it in terms of inductance, the equation we just came up with, negative L di dt. If we bring these two equations together, the negatives will divide out, and I'm going to get an N d phi dt is equal to L di dt. We get a dt on both sides. I'm going to get rid of my calculus. N phi equals L times I. So L would be equal to N phi over I. And that's for just a simple loop circuit. Inductors. There's a picture of all kinds of inductors. If we were in the classroom, you would be pulling those circuit boards out one more time to look at them and find inductors, and we would ponder observations of those. An inductor, usually they are solenoids or toroids. They are basically coils of wire in one form or fashion, and their job is basically, in the simplest sense, to fight the change, to set up a back EMF that keeps everything kind of even keel and fights when the current spikes, fights when the current drops, fights that change. So by comparison, we have inductors, we have capacitors. A capacitor, in the simplest sense, is a circuit device, and it stores charge. And in storing that charge, it stores energy. And it stores that energy because we set up an electric field. So a capacitor is a device that stores energy in an electric field. An inductor is the counterpart for a magnetic field. An inductor specifically sets up a magnetic field. And in setting up a magnetic field, when placed in a circuit, it will store energy in that magnetic field. So, kind of counterpart, one stores energy in an electric field, the other stores energy in a magnetic field. So then, putting this circuit element into an actual circuit, an RL circuit. R is a resistor, L is a symbol for the letter symbol for your inductor, and your coily kind of design right there. That is the circuit symbol for an inductor. So we have a resistor, we have an inductor. We are going to first of all close the switch to location A. When we close that switch to location A, I'm just going to draw a line across there because I'm probably not going to be able to grab that small one. That means this center line is pretty irrelevant there. And we have three things in our circuit. We have our battery, we have our resistor, and we have the inductor. We want to analyze this because we know what the inductor is going to do. It's going to fight the change in the current. So when we throw that switch, it is not going to want that current to increase. If it doesn't want that current to increase, that means that our current isn't going to just pop right up to that maximum value, but it's going to increase gradually. If we ponder that with a graph, we're going to get an increase in current like that, and we're going to approach that maximum current as an asymptote. And so what we want to find, our goal in this situation, is to be able to solve for an I of t equation. So what we're doing here is very similar to what we did with RC circuits, but it's the magnetic parallel. So then we're going to apply the loop rule. Total of the voltages across each element in the circuit have to add up to 0. So then three things there. Voltage of the battery, EMF. Voltage across the resistor, Ohm's law, IR. Voltage across the inductor, L, DI, DT. And our total is going to be 0. So now if we consider the signs of these, well, your battery is a positive because it supplies the voltage. Your resistor is going to dissipate, and because it dissipates, it'll have a negative. And your inductor stores energy, and because it stores, it's removing it temporarily for the circuit from the circuit. That will also be a negative. So now what we want to do in this equation is solve for an I of t function. So then I'm going to do some algebra. I'm going to keep the EMF minus IR on one side. I'm going to move the L di dt to the other side. I'm going to multiply the dt to the other side, so we're going to get EMF minus IR dt is equal to L di. And then I'm going to move things onto their appropriate sides. I need this term to go over there because there is an I in it, and I need the I on the other side with the DI. And anything else, I'm going to move over to the other side. So then when all the dust settles, we're going to have a 1 over L dt is equal to 1 over E minus IR di. Well, we've got the i's isolated on one side. We are ready to integrate. So if we integrate both sides, left side, well, let's ponder endpoints of integration first. So we close the switch. That's a time of 0, and we're going out to some random time t. On the other side, when we close the switch, our current starts at 0, and at some point in time later, we're going to reach a value of I. That's the I of t function we're solving down for. So then the left side, easy to integrate. We integrate, because everything's a constant, we just get a t over L. We plug in our endpoints. It's still t over L. Now, the right side, if we integrate, we're going to have to use U-Substitution. So I'm going to come over here, U-Substitution. We're going to let U equal E minus IR. du di would be a negative R when we solve down. Di would be a du over negative R. So when we plug all that in on the right side, we're going to get the integral of 1 over U du over negative R. I'm going to throw that negative R to the other side, so negative RT over L. And on the right side, we get the integral of U to the negative first du. That's easy, natural log, so negative RT over L, natural log of U evaluated on our endpoints, throwing the expression back in. Hopefully our screen doesn't get too small. Negative RT over L, natural log of E minus IR, endpoints of integration, pulling those from above, 0 to I. So when we plug those in, we're going to get negative RT over L equals natural log of E minus IR minus natural log of the EMF. Writing that as a ratio, negative RT over L equals the natural log of EMF minus IR over EMF. Raise it to the base E, so E to the negative RT over L is equal to E minus IR over E. You can do the rest of the algebra there. Our final equation here, when we solve for that I, is going to be I of t is equal to EMF over R, 1 minus E to the negative RT over L. So we've got our equation there. So basically what happens is what we discussed on the graph originally when we started this. You have your I here, your T here. Instead of spiking, your current gradually increases, and it's approaching a maximum of that EMF over R value. Now, as it increases in current gradually, what's happening doesn't increase right away, is that you are storing energy in that inductor. So eventually, after an infinite period of time, when you reach that steady state situation, you have the inductor now just basically behaving as a long wire, but it has stored energy. When we flip the switch and we close the switch to B, well, let's change our circuit a little bit here. If we close the switch to B, now our switch is down there, which means all of that stuff is gone. Now we have a circuit that is only our resistor and our inductor, and our battery is cut off. You would say, well, if the battery is cut off, we should have no current. That's false, because what happened was when we closed the switch to B, current was originally at its maximum, and now it wants to drop to 0. But as it tries to drop to 0, your inductor fights that. So then your inductor returns, I don't know if returns is the best word, but it works, returns the energy that it stored in that magnetic field to push the charges, to keep them moving until it has exhausted its energy. So instead of the current dropping off instantly, then what happens is your current, when you throw the switch to B, starting at that maximum value, it decays. And it approaches 0 as an asymptote. So then the equation, similar logic to what we did with RC circuits. I'm not going to go through the whole derivation. I of t, when you close the switch to B, is going to be that original maximum current, e to the negative RT over L. Now, in and amidst here, let me squeeze in somewhere We never use Brown. We use Brown. Time constant. Your time constant here, so that we can follow the same logic. In the RC circuits, it was e to the negative t over RC, or negative t over the time constant. So we can think of the time constant in the denominator of the exponent. That time constant is equal to an L over R, the inverse of the R over L that is in the exponent. Your logic of applying it is the same way. It gives a certain percentage of the rise of the current or the decay of the current, depending on which way, if the current is increasing or decreasing. So, an inductor in a circuit will fight the change. It will fight any spikes in current. It will fight any decays in current. It will tend to keep things more even keel. Now, the next thing we're going to get into is wrapping things up in applications of RL circuits. Ponder physics.